have to deal with one more presentation from myself later on. So that's Mario. We're circling back to
Hello,
PSI.
Stefan.
Hello. Thank you much
Yes.
for presenting.
Thank you very much
So
for the
that's
introduction.
very, very clearly a first. So we never had anything about silicium separation or silicium-32 work. So yeah, silicium-32 separation from vanadium targets. That's a very, very first. So very interested to hear more about that. Thank you much for presenting, and the floor is yours.
Yes, I'm just going now to check because the Mac just needs some permission first. Can you help me if you can now see my presentation?
Perfect.
That's
Yeah,
perfect.
brilliant.
Yeah.
Thanks a lot. And yes, as Stefan nicely outlined, thank you very much. Anyways, also NPL for hosting today's meeting. I'm going to talk now about my PhD project. It's called Radiochemical Separation of Silicon-32 from proton irradiated vanadium. And this is part of a main goal that we are following in a project, which means we want to go towards an accurate half-life determination of this isotope. To begin with, I'd like to give you, as you can see, a very short introduction coming over to the results and also give you a very concise conclusion to end my talk. So to go ahead with the introduction, we of course think of why radioactive silicon and why is it of great interest. So its origin in nature arises from the cosmological origin here, which means that it's produced in the atmosphere by the spallation of 40 argon, while subsequently it's deposited here, for instance, onto terrestrial sediments via snow and ice. However, it's of very great interest because if you look at this regime where it's usually deposited, a lot of environmental sciences think of using this one to fill a current dating gap, which you can see here exists between 100 to 1000 years. So with its predicted currently half-life of 150 years, silicon would definitely fit into this gap, which is the reason why it's of great interest here. However, the problem is, that's what a question mark is here, its half-life is actually very imprecisely determined, which is due to the fact that we only have very little sample material. So as you know, in the radioactive community, usually only countable atoms and spread over a sample material in the terms of kilograms, let's say, or grams, it's not very much to be used for experiments. So the reason is then as a challenge, the lack of sample material subsequently yields for the past measurements that have been performed, you can see here from the later 70s until now, to a rather difficult picture when it comes to a precise determination, because a lot of values are quite scattered. And in addition, you can see here some uncertainties are way above 10 to 20%. So the problem is now we have the challenge of lack of a sample material, how to overcome this challenge. And in this way, of course, as usual, we go ahead with the artificial production of a vanadium target here. So by producing the spallation of vanadium, we were able to produce silicon-32 at PSI's high-intensity proton accelerator over the duration of proton irradiation for about 2 years. So by having now proton-irradiated vanadium disks, I can now go ahead to the results. Taking such a proton-irradiated vanadium disk, it's initially dissolved in 2.5 milliliters 8 molar nitric acid as a cocktail with the same amount of 8 molar HCl. And then its pH is adjusted with water to approximately 100 milliliter, yielding 0.5 molar initial molarity. The addition of hydrazine is necessary to reduce its main component vanadium to the preferred oxidation state of 4. When we think now of our silicon-32, once it's in solution, at the very low limits in terms of mass we're working, we consider here the silicon to be actually in aqueous conditions as so-called orthosilicic acid. In the beginning, you can see we use an ion exchange chromatography, the DAUX50, to remove the bulk of the matrix, which is vanadium, which is very nicely visible usually because it forms a very dense blue color here. In the elute phase, however, you see that silicon always runs through as orthosilicic acid because it's neither deprotonated but protonated, meaning it's just a neutral species. However, after the elute run through, so after the first separation, we usually have always some impurities like titanium and scandium and niobium for which I talk about later. Focusing on the silicon again, we usually, before we do the radioactive sample material, we usually work with so-called model solutions. And in this way, you can see, for instance, that we are also able to follow silicon's behavior throughout our system. In general, what you can see here, that our load comprises of 100 milliliter of solution, and we, in addition, add a wash of 20 milliliter, which allows us, you can here see very nicely, to quantitatively recover all the silicon using our DAUX50 separation scheme. Going back to the mentioned impurities, also thanks, of course, to the great work from Trischem, we were able, for instance, to separate the traces that we found of titanium and scandium with the LN resin. And by evaluating the possibility of the monophos resin, we learned that it has actually also high selectivity towards niobium-94, which means for us that in this case, our key aspects for reliable separation schemes have been fulfilled, which was remove majority of the matrix and specifically targeting these impurities, which was for us then, of course, a so-called purification step, whereas the first one is rather only the bulk separation step. To continue with the monophos resin, it is also a short story to tell that I came along the tritium column, which is also provided by Trischem, which is based on Diphonix resin. And in the short here in the analysis of the data that they provided, I saw that actually it works very well, for instance, to remove iron, but of course also niobium. So in our case, you will see we just built ourselves a bit an own tritium column according to already the findings of Trischem in this way. You may think of, I'm talking all the time about vanadium. Why would I be interested if it's also spallation involved of elements which have a higher mass? Or actually, where is this niobium coming from? Well, this is also something we evaluated by making an analysis of our initial material. So we used cold, that means unirradiated vanadium disks, and classified them in terms of cleaned, rusty, and average, which you could usually see visually when you were looking at those disks before placing them inside. And also here, thanks to Dr. Natalia Gazilova from the EPFL Valais, it's the facility of mass spectrometer and elemental analysis platform. So here we were measuring actually, or I show you now ICP-MS results, where we first checked how precisely we could see if there is a content change in aluminium and iron. But more importantly, we used these results to reference a semi-quant analysis. You will see aluminium is, for instance, 0.012%, and it fits quite well here in the range of our measured, quantitatively measured sample, plus 0.003%, which also comes into the range. So this was for us a good reference in terms of semi-quant, which allowed us to say, well, these traces of niobium, molybdenum, and nickel we do see here are really present. And in the process of spallation, we have also the neutron activation, which means these elements, initially, of course, stable, are then just transferred via neutron activation also into their unstable radionuclides. The same applied also to silicon, because we were interested how much initially of cold silicon is inside, whereby here we just sticked, of course, to the stable 28 and 29, not only because of the higher abundance, but also if you're familiar with the system of the MS, as also Ben showed us today, that we usually deal with a lot of interferences, mainly here in the 28, not that many as opposed to 29 and 30. So in here, we were more reliable in the terms of 28 to 29. If we go back to our initial separation scheme, of course, we're not yet at the end. So after the purification of removing niobium and titanium, we were left with something that we didn't see for a long time, or we didn't think about, but of course, it's the gaseous radioactive elements, which is tritium and the both argon nuclides. So our approach here is taking the silicon fraction, performing an evaporation to dryness on PTFE dishes, and afterwards, we are left with SiO2 that we recover with the hydrofluoric acid, which means that each disk is or yields in one fraction, and the final acidity is set in 20 mils to 0.1 molar HF. Obviously, what happens to SiO2 is that in HF media, it's transferred into the hexafluorosilicate anion. And in our, or using our conditions, we were then capable of using the anion exchange chromatography to, under these conditions, not only remove further any other cations like sodium-22, but also pre-concentrate our silicon, which means you can load onto the anion exchanger several of these fractions, which allows you to gather more activity on one column. Then this yielded, in our case, to our final silicon solution, which of course also had to be analyzed further. We do in-house with our quality control. And in the case of the silicon fraction, we are usually analyzing it by liquid scintillation counting. And talking about silicon fractions, there is, you can see in green, after the separation on the DAO-X1, X8, you have here the green, very clear signal of only silicon at the maximum energy, and a very, very slight contribution of phosphorus that we were calculating or deriving to be less than 1 per mil, which means it was a super nice also separation from its daughter, phosphorus-32. To actually confirm that this is silicon and nothing else, you expect, as we also saw today, after an ingrowth time, which is here to be set plus 92 days after separation, that its daughter phosphorus-32 should also grow in, which you can clearly see by having now the higher energy region much more pronounced, which is also that you can see not reaching the maximum energy due to the chemical or in general due to quenching in the LSC. Moreover, long-term gamma measurements were performed, usually in the range of more than 100 hours, which you can see here yielded then always, luckily, only a background spectrum. So we were not able to see any other elements than the expected background elements that you also see when you perform a background measurement over the same 100 hours of time. In the anion exchange chromatography, I also want to give you a bit more deeper insight why this is a very important step for us. So as I mentioned, we were able to pre-concentrate it. This we did, of course, by just doing KD studies for the anion exchange resin, where you can see that in the 0.1 molar HF, we have a fairly high retention of 10 to the 3, whereby elution was later on chosen to be 0.5 molar HCl, as we are going below the 10 to the 1 DG or distribution coefficient, which allows us a very fast elution. It's noteworthy here to mention that we used HCl instead of HNO3 because we also want to do long-term measurements with such a solution in LSC, and HNO3 rather tends then to attack the organic solvent. So in this case, yielding or looking at the sample stability, we were concerned using HNO3. That's why we were focusing our studies on the HCl. Moreover, also important to mention, when I talk about ICP OES or our measurements in the cold system, we equipped our ICP OES, it's an Agilent 5110, with a PTFE sample introduction that also includes a PTFE torch, so that we were usually able to always exclude a silicon contribution from outside, which is of course very important if you also want to provide reliable data, for instance, on the KD studies. To continue with the ion exchange chromatography, this is part 2. We also studied the behavior of the matrix element vanadium with silicon in terms of what happens while you load the fraction onto the anion exchanger. And you can see that's actually favorable because already using 0.1 molar HF, the initial solution, you get rid of a small amount of vanadium, which means that the matrix material is also already eluted while loading the fraction. Moreover, you can see here, we also studied more HCl concentrations with actually respect to both sulfur, vanadium, and silicon, which I will come up soon, is a very important fact when we are talking again about ICP-MS and so-called isobaric interferences that we also learned recently from Ben as well with technetium and ruthenium. If you look at the graph here, by elevating the HCl concentration from 0.05 molar here to the 0.10, sorry, you see that both vanadium and sulfur is completely eluted, while minor losses of silicon occur at higher concentrations. But as outlined by our KD studies, we manage with 0.5 molar HCl to nearly or actually quantitatively recover all the silicon that we wanted. How does this help us further? in principle, we know that after irradiation, an isotopic abundance of sulfur is not anymore the one that we wanted, if detected. But what would be even more better for us is to not have the same mass. So silicon-32 and sulfur-32 is also very bad for MS. So we actually want to remove all the sulfur out of the system. And how did we do this? We implemented a so-called sulphur wash with adding 30 milligrams initially in this fraction and eluting it by the increased HCl concentration. And here, in addition, adding a more or less buffer between the sulphur wash and the silicon fraction, which really removes quantitatively all the sulfur that we got. And this yields eventually our nice silicon-32 fraction. To come back to this nice graphic, we actually then not only studied back here the elution of sulfur, but with the same principle, we could confirm that we also removed quantitatively phosphorus. So maybe being both a phosphate and a sulfate, having a similar chemical behavior, we can here conclude that we were managing to remove both species at once. Very interesting is also the aspect of the pre-concentration, which you can see here that we yielded a separation, or after the separation, activity concentration of approximately 110 kilobecquerels per gram, which you can imagine using 20 milliliters as final fraction is equivalent to over 2 megabecquerels of silicon-32. And this is several orders of magnitudes more than ever reported in any literature. Knowing here again, we were actually targeting sulfur-32, but as mentioned, here we are actually able to also remove the phosphorus here, which is the daughter, quantitatively. In addition, this summarizes the scheme a bit better from our recent publication, in which you can just follow our scheme, of course, also a bit better. But the very important tasks have been also done by the help of Trischem with the cation exchange resin. And also we were very glad to find the two specifically designed resins, the Ellen and Monophos, because they were helping us to tackle really these two problems, having the titanium and niobium impurities all over the place. To finalize now my presentation, I come to the conclusion and want to outline what I hope you got from me today as a take-home message, that silicon-32 is a new chronometer for nuclear dating. Its forcing application, once the half-life is determined more properly, let's say, is environmental sciences to fill the dating gap between 100 to 1000 years. To do so, we at PSI artificially produced the silicon-32, and having not only 6 disks processed, but approximately over 150. Currently, we have a stock of around 20 megabecquerels, which is, as you can see, a worldwide unique amount. And our chemical separation process was sufficiently applied and showed both highly selective, but also being very robust in this case. Last but not least, the half-life determination is currently ongoing. We already received some values, but of course have still to finalize to get or to obtain the best lowest uncertainty. So this is not yet finalized, but of course we are working with our partners very intensively. In this way, I thank very much not only the persons involved in my daily life, but also being today at the user meeting. Stefan, thank you very much. Also, please tell Alice, thank you very much as well for being always helpful. And your whole research and development department for giving us the nice resins. And of course, I hope you enjoyed the talk and looking forward to receive your questions.
Thank you very much. Very interesting presentation. 150 disks, that's quite a bunch. So
yeah, that's quite a bunch, yeah.
You've been doing lots of chemistry, and especially you had to take out a lot of different elements. So that required a very, very thorough chemistry indeed. So congrats. Very nice.
Thanks. Yeah, that was also a lot of fun, of course.
Okay, so are there any questions at the moment from the audience? Again, otherwise you can always shoot an email to Mario. So are there any questions? So okay, there's a question from Hossam.
Oh, yeah.
Why did you choose vanadium disks? only?
Yes, a fair point. Vanadium is, in our case, used because, first of all, it's a metal. For instance, we are not allowed to use, as our competitors, as they do in Los Alamos, to use, for instance, potassium chloride, because it's a salt, and this could eventually dissolve in the cooling circuit. So we had already prerequisite to use a rather solid or stable target material. And vanadium came up because it's, first of all, also having a natural abundance of being monoisotopic with the mass 51, nearly 99.75%. But also they calculated that the main spallation product is then actually silicon-32. So this was then used under the assumption of nuclear reaction that we will have actually a high yield of silicon-32. If this answers the questions.
Yeah, actually, there's another question by Ben Russell. Yeah, that fits. So very interesting presentation. Have there been many previous attempts to measure the half-life of this lithium-32?
Yeah, may I share again quickly the presentation?
Yeah, sure.
Because it might be interesting if I can go back to this slide. There have been various attempts, and the current half-life is based, as usual, on a given average of all these values. The problem is that currently it's, let's say here, is a small choice of half-life values, which have been summarized by Fifield and colleagues. And you can see that it stopped somehow in the late 1990s. So they're not very recent values, but in the past, you see it's 1, 2, 3, 4, 5, 6, 7, 8. In total, I think around 14 values are available, but they're all scattering and are not showing actually a clear evidence for narrowing down this value.
Okay, thank you. Okay, so Ben has his answer.
Mm-hmm.
Are there any other questions? If there are no other questions, then again, thank you very much.
Thank you very much too.
Yeah, and